Assalamu alaikum wa rahmatullahi wa barakatuh. This is the presentation for the course CSC 3304 Machine Learning taken by Dr. Amir. This presentation concerns our group project. My name is Muhammad Rashid Saleh Batha, and on this slide you can see the names and matric numbers of the rest of my group members for the purposes of the record. The objective of the project is to determine and implement a hybrid machine learning algorithm to solve a particular problem, and we will go through how the model was built and how we used it to solve the problem at hand. Now let's move on. As for how the presentation is structured, we'll begin with the introduction, where context will be provided about the prerequisites regarding this project, background and the objectives, after which we'll move on to methodology, where we explain how the problem was solved. And finally, we can discuss and break down the results. Beyond that, we can conclude with the findings and the challenges, and also scope for potential improvement. Let's move on to the project background. Let's talk about the dataset. This dataset is provided by the City of Austin's Open Data Initiative and details the Austin Animal Center's shelter pets and their respective outcomes. The original dataset lists the details of all the species under the AAC's care, which includes cats, dogs, and even some bats. However, a more refined dataset, which is derived from the original, containing only the details of cats, will be used for the purposes of this project, courtesy of Aaron Schlegel. This dataset contains 37 columns and 29,421 records. Now, the objective of the project is pretty straightforward. As I mentioned earlier, the objective of using this dataset particularly is to predict the outcome of each animal based on the features at our disposal. The outcome is what ends up happening to the pet, be it adoption, returning to the owner, or even death. Machine learning is employed to solve this problem, as it will be most effective in figuring out which parameters have an effect when it comes to the outcome. The rationale of this object is simple. If there are any visible patterns or trends derived as a result of our investigations, it will help optimize for the outcome that is preferred, which is adoption. Certain parameters are within the AAC's control, so the knowledge obtained will allow them to curate those parameters. On the other hand, the parameters not within the AAC's control will hopefully assist them in allocating resources in the right place. Now, the secondary objectives are to figure out which parameter has an effect on adoption rates, and there is a high-level objectives, which is to utilize feature engineering and hypertuning to create a better model. Now, on to methodology.
Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. I am Tanvir Mahmood Hassan. So, today I am going to present the literature review, which is the subcontent of methodology. In this project, we would like to use the random forest approach, which is quite straightforward. So, it is a supervised learning algorithm which uses the approaches of ensemble learning for classifications and regression. So, in these sections, I will discuss how random forest will work. So, if we see this picture, we can see this is the dataset, and random forest randomly choose the dataset and created decision 1, decision 2, and decision 3. Here we can see that the most of the majority voting or the average of the prediction will conclude with the final result. So, however, there is no interrelation between this tree while constructing the trees. It works by building a multitude of decision tree at training time and giving output, which is a mode of classification and regression. It can combine the multiple prediction. We have decided to use random forest method because compared to other algorithm, random forest give more accuracy. Now we will discuss the advantage when compared to the decision tree. So in first problem, we can see that decision trees are too much sensitive. And the second problem is that if we alter the training data, and the prediction can be slightly different in turn. And the third one is costly. And the fourth one is decision tree has the risk in overfitting. And the fifth one is decision tree appear to find local optima because after splitting it cannot be undone. And the sixth one and the last one is that decision tree work on the whole data set that uses all the column or feature, but the random forest work on the based on randomly selected observation and a specific column or feature to build numerous decision trees and then make a conclusion with the average of the result. So the next section we will discuss by brother Hazik.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Haziq Adli bin Zamzuri, and I'm going to explain about the benefits of random forest compared to decision trees. So the first of all is random forest is suitable for any requirement, whether the model is regression or classification task. That's one advantage of random forest. So the next one is random forest capable of handling numerical functions, binary features, or categorical data. Even though there seems to be a little pre-processing that must be conducted, there is no need to transform or rescale the data. So furthermore, decision tree is considered as a weak learner since it cannot make great prediction on unknown example, even though it does very well on training data, which also known as overfitting. So by combining multiple trees into forests, the random forest algorithm will enhance the predictions of our model. So this method is called ensemble methods, which use multiple learners or algorithm and group them together to create a stronger machine learning model. So in case in our project random forest, they are ensemble of multiple single decision trees. Decision tree contains a low bias. Low bias means low training error with high variance, which means high test error. So random forest algorithm will average all the decision tree in the model as well as averaging the variance, resulting in a low bias and moderate variance machine model. So next one is challenges of using random forest algorithm compared to decision tree. So the first of all is model interpretability. Random forest model are not at all interpretable. They are like black boxes. Although random forest model don't offer as much interpretability as a single tree, their performance is a lot better, and we don't have to worry so much about perfectly tuning the parameters of the forest as we do with individual tree decision trees. And next is time series. Random forest algorithm cannot perform well when data is form of a time series. So the last one is memory and overfitting. So for a very large data set, the size of tree can take up a lot of memories, and it also can tend to overfit. So we should tune the hyperparameter well so that it can avoid the overfitting.
Assalamu alaikum. I am Muhammad Yasin, and I will be explaining the hypertuning section of our project. So in order to squeeze out a little bit of more accuracy from our model, we decided to change the hyperparameters of the learning model, in this case the random forest classifier. Now there are several parameters that can be tuned in a model. Random forest classifier also has its own set of parameters that can be tuned before using it to train on our data. Among them are the ones you can see over here. The first one is an estimators, which defines the number of trees that is going to be created in the forest. This is a major part of the random forest classifier. The number of trees influences how well the classifier fits our data. without overfitting based on just certain features. The next one in the list is the maximum number of features that are considered for splitting a node. In a decision tree, the splitting of node at each level is done using a subset of features. This parameter defines the maximum number of features that may be considered in any such split. Moving on, we have another parameter that is also related to the structure of the tree, the depth. The depth of the tree is basically the number of levels that may be formed in the tree. The maximum depth parameter limits this number to a threshold, so that none of the trees exceed that number. Min samples leaf is a parameter that defines a criteria for the leaf node. It says when the tree is complete, its leaf nodes should at least be describing the given number of data points in the whole dataset. This is therefore an important parameter to prevent overfitting in a model. If the leaf node only describes, for example, a single data point in the whole dataset, then that is too specific and may be a result of overfitting. Lastly, bootstrap is a fancy parameter name that basically tells whether the data point should be sampled with or without replacement. Setting it to true means with replacement, and setting it to false means without replacement. Now these are a lot of parameters. Tuning each of them manually would be very tedious. And when it comes to hypertuning, the best approach is to just brute force and find what's the best. Wouldn't it be better if you could just tell the machine what range of parameters to check for each of them, and it checks all the different combination of the values in the range and returns it to us? That is where grid search comes in. Grid search does exactly what we wanted, that is trying out different combination of values of the parameter given a range. After it exhausts all the possible combinations, it returns an object holding the information about the search, including the best parameter combination. We could straight away use the best model from the object, or we could retrieve the parameter list and pass it to the original classifier and model it manually by retraining it on our data. However, there is one unsurprising problem with this approach: overfitting. Since grid search is trying all the possible combination of the parameter values on a defined training and testing set to get the one that performs best, it is highly likely that the best parameter combination of values found by grid search is only best for the training and testing set it was evaluated on. Thankfully, there is an easy way to resolve this, by using cross-validation. Cross-validation is an effective way to prevent overfitting. It segments the data into a defined number of folds. The model is trained on all of the folds but one, and then evaluated on the left out fold. This process is repeated as many times as the number of folds. The average of the accuracy for each iteration is then taken as the summarized cross-validation score that can be used to adequately compare different models. As you can see, this process manages to escape the problem that we had before using cross-validation. That is, using the same training and testing set for every model. Scikit-learn's grid search class actually has cross-validation integrated, which saves us the trouble of doing it separately. So now that we have gone through a brief overview of the method used for hypertuning our model, let us look at the results. For our model, we define the set of values shown here beside each parameter as the range for the corresponding parameter, and also the number of folds for cross-validation was set to 3. Running grid search with these parameter values took 28 minutes on Google Colab, a pretty long time. The accuracy of the best model found by the grid search showed a maximum of 2% increase, give or take the randomness involved, which is not quite significant, especially given the time taken to carry out the grid searching. However, it should be noted here that grid searching and hypertuning is usually the last trick under the sleeve that is used to improve the accuracy of the model. Therefore, it doesn't usually result in significant increase in the accuracy. But nonetheless, it was a learning experience for us throughout the 3+ hours of researching that we went through, including attempts that went wrong and results that got lost due to Google Colab resetting. And that's all from me. Thank you for listening.
Alright, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Badruddin bin Saleh, and today I'm going to present about principal component analysis, which is to select the most important features in this data. So before that, let me explain some variables that have been selected before. So this variable have been selected just by thinking logically, which during the previous process. So this variable is the code, sets of the animal, the speed or nature, CFA breed, breed 1, breed 2, and outcome days. So the target of this model is, the target variable of this model is the outcome type. So the first step before doing PCA or principal component analysis, we're going to standardize the data. So in this particular model, we're going to use z-score to standardize our data, which the value minus mean of that particular column divided by the standard deviation of that particular column or that particular features. Then we will obtain the z-score for that tuple. And the next step is we create covariance matrix, which is a 7 by 7 matrix since we have 7 variables. This matrix can be created by pair up all the features, means features 1 will be paired up with features 2, features 3, features 4, and etc. And this will create a 7 by 7 matrix. So the second step of the next step will be to find the eigenvalues of that particular matrix. So these eigenvalues will be the principal components of this principal component analysis. And the next step is the eigenvectors. So eigenvectors for these eigenvalues will hold the importance of each features in that particular principal components. So this will be explained later. And finally, we select features. First, in order to select features, first we will select principal components, the most important principal components, and then we select the features, the most important features inside the principal components. So the result of the analysis is the ratio of all principal components, which means PC1 and PC2. PC1 achieve 0.24, PC2 achieve 0.17, 1661, and etc. So the higher the value, the more ratio of that particular principal component. So we will choose the best two highest PC in this project, which we will choose PC1 and PC2. So let's see the eigenvectors of these eigenvalues. Let's see the features vector of PC1 and PC2. So this is the features vector of PC1 and PC2. So the value at the top 0, 1, 2, 3, 4, 5, and 6 here represent the variable of the data. So PC1, we look at the highest value in PC1, which is 0.66, and 0.6 also 0.66, which is for features 3 and features 5 here. So features 3 is breed 1 and features 5 is CFA breed. So we will choose these two highest variable, and for PC2 we will choose features 1 and features 2, which is speed or nature and outcome age days, since these features achieve a higher score in this particular principal component. So after we train the model by using only those 4 selected features,
So the result of this PCA, if we train the model without doing PCA, means without we train the model by using all those 7 features, we achieve the testing accuracy of 79.84%, while training accuracy is 84.45%. And if we train the model with only those 4 selected features, we achieve testing accuracy of 81.2% and training accuracy of 81.67%. So we can see the performance is slightly increased by 1% to 2% rather than using all the features, means without performing PCA. So it seems like if we choose all the features without doing feature engineering, this might cause overfitting of the model, since the training accuracy is 85%, almost 85%, while the testing accuracy is only 79.84%. Though the model shows improvement here, there is still a doubt whether it is good to use PCA on this such of categorical data.
Let's talk about the final results. Now we will utilize a standard suite of performance metrics to evaluate a model. They are accuracy, sensitivity, sometimes called recall, specificity, and precision, which is also the positive predictive value. For our model, we got an accuracy of 82%, sensitivity or recall of 82% as well, specificity of 73%, and precision of 83%. To provide further context to the results obtained, let's look at the implications. An accuracy of 82% is certainly quite impressive, but it does not usually tell us the whole story. For that, we will need to look at the other metrics. Sensitivity or recall is an indicator of how many of the actually positive cases that was flagged correctly. Precision, on the other hand, is an indicator of how many of the flagged cases were actually positive. High sensitivity tries to account for false negatives, while high precision tries to account for false positives. Specificity fulfills a similar role to precision and is often at odds with sensitivity. As mentioned before, accuracy is not a good one-size-fits-all solution when it comes to performance metrics. The other metrics provide nuance and is highly contingent on the problem we are trying to solve. False positives do not always hold the same weight as a false negative. In our context, a false positive implies that a cat that would not have been adopted was classified as such, while a false negative implies that a cat that would have been adopted anyway was classified as one that would not have been. It would be assumed then that the cats that are at a higher risk of not being adopted would receive more attention. Therefore, false positives here have a greater impact than false negatives. This is why it is better that our model optimizes for specificity and precision rather than recall, which it does. Now, let's talk about and discuss the various findings and challenges that were encountered during this project. Apart from the variety of soft skills that we learned by working together, like communication skills, management, and collaboration, the relevant learning outcomes have to do with the implementation of the solution. Generally speaking, the specific techniques we use to improve the accuracy of our ensemble method, like feature engineering and hyperparameter tuning, resulted in small improvements in accuracy. The question that needs to be answered is, was this small 2 to 4% improvement worth the computational and time costs? Using principal component analysis to improve feature selection does improve the performance, but the efficacy of using it, especially with regards to categorical variables, still remains to be seen. We have doubts about whether it was useful in the long run. Moving on to hyperparameter tuning, specifically using grid search. Grid search was highly time consuming to use, and thus only a few parameters were defined in the range. This brings the value proposition into question because the improvements in accuracy was only marginal. And then again, we didn't know in advance whether these techniques would result in massive improvements in accuracy, so it was more of a learning experience regarding what works and what doesn't. As for future works and scope for improvement, some potential avenues of consideration are using the high correlation filter instead of principal component analysis for feature selection, using random search instead of grid search over a wider selection of parameters to reduce the cost, especially with regards to time. And finally, of course, we could always try another combination of machine learning models and develop a hybrid that could potentially better solve this problem. And that marks the end of this presentation. Jazakallah khair for listening. Assalamu alaikum wa rahmatullahi wa barakatuh.